This lecture is on a concept called the perfectly matched layer, very often called an absorbing boundary condition. And as you'll learn, it's not a boundary condition at all. But it's a technique to absorb outgoing waves. And you've already seen some movies of that. There'll be more here. I think the perfectly matched layer is the most difficult thing in finite difference time domain. It's not so much that the perfectly matched layer is difficult to understand. It is a little bit challenging. But this really gums up the update equations. It makes them much more difficult. What we've derived so far for update equations have been pretty simple. Once we incorporate a PML, they get a lot uglier, and they involve integrations and things like that. So this lecture, we won't be deriving the update equation. We'll just be talking about the concept of a PML and how to incorporate those variables into Maxwell's equations. In the following lecture, we'll pick up with those equations and then march through and derive our big complex update equations that incorporate this perfectly matched layer. So we'll review what happened last time. I definitely need to give some background information before we can understand this perfectly matched layer. Then first we'll introduce what is called a uniaxial perfectly matched layer, and it'll make sense why we call it that when we get to there. Then what is more state-of-the-art in finite difference time domain right now is a stretch coordinate PML. And the transition going from uniaxial to stretch coordinate I think is very logical. If I just started talking about a stretch coordinate PML, it really wouldn't make much sense. Then when we're done, we need to talk about how we calculate the PML parameters. We'll be building in loss and controlling impedance in the outer boundaries, so we have to understand how to set our parameters. And I'll introduce one recipe for doing that. And then the last thing is how we incorporate our PML into Maxwell's equations. And we'll end this lecture there. And next time, we'll pick up on Maxwell's equations with the PML and really follow the same outline we've done before. But now we have a lot more terms and some more complex things happening. But we'll ultimately derive update equations. And they'll have the same anatomy as they've had before. From last time, we talked about windowing, and essentially we can only run our model over a finite number of iterations. We can't run it out to infinity. So it's really like we've taken the impulse response we would record if we did record out to infinity and multiply that by a window. And point-by-point multiplication in the time domain becomes convolution in the frequency domain. And this really means we've blurred our frequency spectrum. And even though we might calculate frequency points that are very close, the blurring really limits effectively how much we can resolve in that frequency response. And we derive some rules for how we calculate the time step and the number of steps to resolve an upper frequency and a frequency resolution. But a finite period time simulation blurs the frequency response. So we had some rules. The time step that we use does not tell us anything about the frequency resolution we will get. The time step completely dictates the maximum frequency that we'll be able to resolve, and that comes from the Nyquist sampling theorem. The next thing, the number of iterations that we use, which we're calling steps here. So the length of our simulation, that is what determines our frequency resolution. And we ended up with a rule. How many steps do we need for our simulation? Well, given our time step and the frequency resolution we want to get in the spectral response, it's just 1 over the time step and our desired frequency response. And of course, we'll round that to an integer. And as long as we have that many steps or more, we'll get that kind of frequency resolution. We also talked about dielectric smoothing. We are potentially fitting curved objects into our Cartesian or blocky grid, and they come out looking blocky or staircased. And one thing we can do is just add more points, but of course that adds more memory requirements, more simulation time. So we talked about smoothing them, and there's just a simple smoothing procedure, but we also talked about how to do this and do an anisotropic smoothing, which is technically better. Although we can get, just with simple smoothing, we can still get improvements on convergence. By smoothing, we can get away with fewer points on our grid. So in other words, it converges faster. So our formulation came down to this. We focused on the constitutive relation D equals epsilon E, and we start off with some epsilon that could even start off as being anisotropic. Usually it starts off being isotropic. Then we construct a normal vector field, and we wrap that into a big matrix. And this is a field that is always normal to material interfaces. And so we develop a whole grid full of these normal vectors, reshape them into matrices, and given that, we can use that to come up with a smooth version of our dielectric. We'll take our permittivity, we'll just smooth it by averaging. Then we'll take the reciprocal, smooth the reciprocal, and then take the reciprocal of that. So we do a double reciprocal smoothing. So we do both types of smoothing, and then we combine them together with this normal vector matrix, and we get an anisotropic smooth dielectric, if you will. So even if epsilon, the permittivity, started off as being isotropic, once we smooth it this way, it becomes anisotropic. Now this technique is a bit advanced, and as I mentioned on the previous slide, we can still improve convergence simply by smoothing but keeping it isotropic and simple. We don't have to do an anisotropic dielectric smoothing. Here's what it looks like by smoothing a sphere. Then we went on and talked about this thing called a 2x grid technique. And we're really tasked with somehow assigning the permittivity and permeability values across our three-dimensional, two-dimensional, or one-dimensional grid. But we know that our field components are staggered, and we assign certain permittivity values to be at the points of the electric fields and permeability values to be at their corresponding magnetic fields. So they're staggered as well. And in fact, if we just use doubly anisotropic or doubly diagonal tensors, so we're just retaining epsilon xx, epsilon yy, epsilon zz, mu xx, mu yy, mu yz, we need 6 big arrays that cover our entire grid that describe our materials. So how on earth do we figure out where all these materials lie on the Y grid? They're staggered. It's crazy. So a way through this is we'll calculate one Y grid. We then double the number of points. It will still describe the same physical amount of space, but with twice as many points. And then we forget about the Y grid for a little bit, and we build our device on this 2x grid. So it's a grid with twice the number of points. And once we have that 2x grid, we essentially just skip every other cell, and we can extract our 6 different arrays on the Y grid instead of the 2x grid. Once we extract all of our arrays, we're done with the 2x grid. We throw it out. We don't ever use it again in our code. It's only a trick to build our devices on the Y grid and sort out where they all lie in terms of their staggering. So here's just sort of a summary of this concept. We have on the left our low res, or just our standard Y grid, and we can see our field components, how they're staggered within the Y cell. But notice how they're staggered. It really looks as if we're getting twice the resolution, and in fact we are. So we can divide all of our cells in half, and each one cell on the standard Y grid is 2 by 2 cells on our 2x grid. And so in this context, it makes sense that we are talking about this 2x grid. We construct it, build our device on it, and then just pull off the values we need by skipping every other cell, like we talked about last lecture. In one slide, this really summarizes how we pull things off. So we've built our device on the 2x grid, and I'm showing how the field components overlay. So we want to build ERZZ. So we look for all the blue circles over here, and we just see, is this inside or outside of dielectric? And so we populate this Y grid based on going every other cell here where the blue circles are. Likewise, we have red arrows. We'll look at our red arrows and pull off where there's material and where there's not. For URXX, we'll look at the green arrows. We'll pull off where there's material and where there's not and populate this. So notice how different these look, but they're all describing this circle in the middle of our grid. And in fact, if we modeled this, it would come out that way. So a little bit strange, but each one of these parsing steps is one line of code in MATLAB. And so it actually is it's much simpler than having to build these three arrays at the same time, trying to figure out where everything lies and doing each one individually. So in my opinion, that's much more difficult than just creating a grid with twice as many points, building the device on it, and then just parsing off these 1x grids from it, or the Y grids. So the 1x grid is the Y grid in my naming convention here. So that was last lecture. Now we're changing subjects and we're going into the perfectly matched layer. There are some background concepts that we need to talk through before we can discuss the PML. First is, what is a tensor? So we'll start off with some vector v, and it has a direction and a magnitude. If we multiply it by just a scalar number, our vector v will still point in the same direction, it just changes its magnitude. Now if a is negative, it will still be aligned and parallel with this vector, it will just point in the opposite direction. So the point is, scalar numbers only change the magnitude of a vector, they do not change its direction. We can generalize that a bit. Let's start off with the same vector, which has some direction and magnitude. Instead of multiplying it by a scalar, we'll multiply it by what's called a tensor. It's just a 3 by 3 matrix, assuming this vector has 3 elements. But this can not only change the magnitude of our vector v, but its direction. We see we have a very different magnitude and direction over here. So how does it do that? Well, if we write our vector just as a 3-element column vector, and this is 3 by 3, what we see is that any one of these 3 components, x, y, z, in our original vector, can leak into any one of the x, y, z components in the new vector. So this 3 by 3 matrix is just a general way of saying anything can happen, and it can change magnitude or direction. So that 3 by 3 matrix is a tensor. Now let's think about reflectance from a surface that has loss. So if we have loss, our complex refractive index is the ordinary refractive index plus this kappa parameter called the extinction coefficient. And if we looked at reflectance from this, so that's how much power, the fraction of power that gets reflected from going from air into this slab, here's our equation. The important thing to notice here is refractive index and loss are both contributing to reflection. So if we have a change in refractive index, that alone is not responsible for reflectance. The loss in the material also contributes to that. Next, we need to look at a bit more complicated case, and these are called the Fornell equations. In the red and blue, these are called the Fornell equations. And this is what describes transmission and reflection for arbitrary polarization and arbitrary angle of incidence. And in fact, the TE and the TM polarizations here reflect and transmit differently at an interface. And we also see that the reflection and transmittance depends on the impedance in either material. So this eta1 is the impedance in the top material, and this eta2 is the impedance in the bottom material. So right away we can see fundamentally it's a change in impedance that causes reflections at an interface. We also see that the angles can change reflectance and transmittance. So if suddenly our wave comes in at a different angle, reflectance and transmittance can change. And then of course we have Snell's law above, which is describing really our angle of the transmission. The law of reflection says angle of incidence equals angle of reflection, and Snell's law just describes refraction. It's the bending of the wave from material 1 into material 2. So these are much more complicated equations, but it says that reflection and transmission depends on a lot of stuff. Next, it will turn out that we will need to make the materials inside our PMLs anisotropic in order to do what we want to do. And we'll get into that. But right now, let's think about how to incorporate anisotropy into Maxwell's equations. And it shouldn't be much surprise from previous lectures. We will make our relative permittivity and the relative permeability tensors. So that lets us write our two curl equations in sort of a matrix form this way, where these big square matrices are the curl operations, taking derivatives of our H fields. We have our 3 by 3 tensor multiplying our electric field. And then we also have our 3 by 3 permeability tensor multiplying the H field. So that's how we incorporate tensors into Maxwell's equation, when the permittivity and permeability become tensors. And this is where we'll need to start when we incorporate our PML. Just for your interest, there's really three types of anisotropy. It always turns out we can choose a coordinate system and some orientation and some oblique angle between our different axes that our tensors become diagonal. So there's only ever really three numbers that we can choose to put into a tensor. The only way we get numbers in these off-diagonal terms is when we're analyzing a tensor in a different coordinate system than it has its crystal axes. But anyway, there's only three numbers in a tensor. And if all three of those numbers are the same, we call that isotropic. And that's really not anisotropic at all. If two are the same and one is different, we call that a uniaxial anisotropic material. And if all three are different, that's the most general case, that is biaxial. So these are the three flavors of anisotropy. Another thing we need to identify is that there's two different conventions for changing your material parameters to incorporate loss. In one convention, we just have a complex permittivity, and that works great for frequency domain models. However, in time domain models, complex numbers aren't something we want to deal with. So instead, we'll adopt a purely real permittivity and a purely real conductivity. And in fact, the two are related. So the epsilon here with the squiggly over it, this is the complex permittivity. And we can write the complex permittivity from our sort of view one, which we use in frequency domain models, to this real permittivity and a real conductivity. So the two are related. And we can put those into Maxwell's equations, and it looks something like this on the right-hand side of this curl equation. Del cross H is sigma plus j omega epsilon times E. And in a frequency domain model, we would just put in a complex permittivity. So in some ways, frequency domain models are a bit easier, but we're doing a time domain model here, so that's the way we have to do it. Now, it turns out we won't need all 9 numbers in our tensors, and it will turn out that we just need diagonal tensors. And so when we just have diagonal tensors, we just have numbers going along with diagonal. So in other words, the axes of the anisotropy here will correspond to our x, y, z axes that we're analyzing the fields. And we're calling these doubly diagonal anisotropic media because both the permittivity and the permeability are diagonally anisotropic. And further, rather than have complex numbers going down the diagonal, we can have an epsilon plus our sigmas. And so we see those two discretely. So our permittivity and conductivity and these bottom two equations are both real numbers. Notice we still have complex numbers. We still have this j omega, and we'll take that into account when we jump from the frequency domain back to the time domain. So what happens then to the Fornell equations if we're reflecting and transmitting off of something that is anisotropic, and specifically doubly diagonal anisotropic? Well, refraction, we modify Snell's law a little bit. And in this case, sine of theta 1 is the square root of b times c sine theta 2. So what is bc? It's two of the elements in the tensor, in the y and z directions, it turns out. What about the reflectance equations for both polarizations? We modify those as well. We still see the angles, but in places of impedances here, we have our tensor elements from the permeability and permittivity. So these really are our Fornell equations when we have anisotropic materials. And this is going from air into something anisotropic. So we'll use this a little bit later. Okay, some final notes on scattering at a single interface. It is a change in impedance that causes reflections. So if we want to avoid reflections, we need to keep the impedance the same throughout the region. Snell's law quantifies only the angle of the transmission relative to the angle of the incident wave. the refraction, or Snell's law, does not depend on polarization. So both polarizations will refract the same. However, the two polarizations will reflect and transmit differently. And we have the Fornell equations, a different set, one for the TE polarization and the other for the TM polarization. And we see that the two things that are important that go into determining how much gets reflected and transmitted are, of course, the impedances, but also the angles. The angles can change the reflection and transmission as well. So we got to keep all this in mind because we want our PML to absorb all outgoing waves regardless of angle of incidence, regardless of polarization, regardless of frequency, really regardless of anything. We want it to just to absorb and not reflect. Okay, finally on to the uniaxial perfectly matched layer. Here's our problem. We have some device that we're modeling, and we want to hit it with a source wave, and we want to see how this scatters. So in other words, we want to see just what bounces off this device. Well, if we didn't do anything at our grid boundaries, this source wave and all these scattered waves would hit the edges, and they would bounce back into the model. And it would look like additional scattering of the device, but it's not additional scattering of the device. It's just something happening at the boundaries. We would like whatever scatters from this just to go off as if it goes off to infinity and not come back in, because then we can see just what gets scattered by this device alone. So the question is, what do we do at our boundaries? Well, clearly, we're going to do a PML. So this is a movie you've seen before in previous lectures. But we have just a simple dipole source that throws power at all of the boundaries, so we can test our PML everywhere. And if you're looking just in the bright green region in the middle, it really looks as if that ring, that radiated ring, goes off to infinity. It's only when we look inside the PMLs that we can see that it is actually decaying. I'll play this one more time. So imagine I was not showing the PML regions. We wouldn't know what's happening. It just looks like the ring goes off to infinity. But looking inside the PML regions, we can see how it decays pretty rapidly. And the ring doesn't actually go off to infinity. It gets absorbed. But the important thing is it does not reflect back into the bright green area, which we'll call the problem space. We have these in practice too. We have anechoic chambers. We might want to install some kind of device. We hit it with a wave, and we want to see how that device scatters. Well, if it's sitting right in front of a wall, how do we tell the difference between what's scattered from the device and what's scattered from the wall? We need some kind of absorbing thing at our walls. And so we use this triangular shaped cone. And the triangular shape really helps taper the impedance from air into whatever the impedance the foam is. And the foam is made of material that's very lossy. So the wave goes into this, it doesn't reflect, it gets absorbed. So this really is a PML. Now for our one-dimensional finite difference time domain, we use this perfectly absorbing boundary. Remember the requirement there. The wave had to travel exactly one cell in 2 time steps. And we specially calculated our time step to ensure that. But now we're in 2 dimensions. Think of what happens here in terms of the speed of the wave hitting this boundary. Let's say we calculate our time steps, so this wave travels exactly 1 cell in 2 time steps. We could have a perfect absorbing boundary for this. However, the same wave traveling at the same speed, but now it's traveling at an angle. Effectively, it's traveling slower in this horizontal direction. And so it travels much less than 1 cell in 2 time steps. So our perfect boundary would not absorb this outgoing wave. In fact, it would reflect it. It would only absorb this one. And of course, if we calculate our time step to absorb this wave, suddenly this first one would reflect. And so when we move into multiple dimensions and we have waves hitting the boundaries at different angles, we can't use this perfectly absorbing boundary condition anymore. We have to do something else. So let's create, maybe in the outer 10 or 20 cells, let's put loss in there. Let's make this kappa term, which is loss. That's the imaginary part of refractive index. That's responsible for loss. Let's just make that greater than 0. So when waves hit it, they get absorbed. That sounds great, right? Remember that reflectance equation. We can build in loss that will absorb waves. However, that loss will also contribute to reflection. And why? Because when we incorporate loss, we're changing the impedance, which doesn't match to our problem space, and we get reflections. It may be marginally better than not having anything there, but we have reflections. This isn't good. We need to do something else. That something else is, at the same time as introducing loss, let's adjust something else so we keep the impedance matched. So remember, our permittivity is complex. There's a real and an imaginary part. The imaginary part, when that becomes non-zero, we're starting to introduce loss. Well, we have a second parameter that we can also adjust to help, as we're introducing loss, also keep the impedance matched. So that's the answer. Let's introduce loss, but also keep the impedance matched. Well, we have some more trouble. Now let's look at our Fornell equations. So here's the reflection for the TE polarization. We want reflection always to be 0. So we'll set this equal to 0. And we're doing a similar thing down here for the TM polarization. But let's look at this. So we're setting this expression equal to 0 because we want 0 reflections going into our PML. So we take this expression and do some algebra on it. And what we see is that we have the two impedances related, but there are these cosine terms. So in other words, the angle thing is really gumming up the works here. We can't have 0 reflection for all angles of incidence. How do I know that? Because there are those angles relating eta 1 to eta 2. If we want to match the impedance over all angles, there shouldn't be any angles there. We should just see eta 2 equals eta 1. And a similar thing happens for the TM polarization. So the conclusion from this is we cannot prevent reflections for all angles of incidence. We'd have to pick some eta 2, some impedance in that PML region, given some angle going in that would minimize reflection, but only at that angle. So that's not going to work for us. We need to do something else. This is where the anisotropy comes in, and I sort of said that up front when I had a priori knowledge. That's where we're going. But it turns out if we make our PML regions anisotropic, we can make a region that matches the impedance for all angles of polarization, all angles of incidence, all polarizations, all frequencies. We can do that if we introduce this anisotropy. So let's set up our problem. We have our problem space, and we'll say that that's air, and we're going into our PML region, which has some, at this point, some magical permeability and permittivity. And we come in at some angle theta 1, and we refract into theta 2, and we reflect at an angle of negative theta 1. What we want is 100% transmission and 0% reflection for all frequencies, all polarizations, all angle of incidence. What do the permeability and permittivity need to look like so that we can do this configuration? That's our problem statement, and this is what the uniaxial PML falls out of this. So really, we want to match the impedance everywhere. So that's our rule. To prevent reflections, we need the impedance matched. What's a simple way of doing that? Well, let's just keep mu and epsilon equal. And as long as mu and epsilon are equal, the ratio will always give us the same number. So we can change mu and epsilon, but as long as we're keeping them equal, we can change them, and the impedance will always stay the same. So mu will equal epsilon, and so we'll just call it S. And we'll let it be diagonally anisotropic. And we're going to derive some rules of what A, B, and C need to be in order to do our PML problem, and that is prevent reflections for all frequencies, all polarizations, all angles of incidence. The first thing we'll do here is let's choose that the square root of B times C in our tensor equals 1. So remember our law of refraction for our diagonally anisotropic media. If we set this square root term to equal 1, we essentially get sine of theta 1 equals sine theta 2, which means theta 1 equals theta 2. We get no refraction. So if theta 1 and theta 2 are equal always, and then we look at our Fornell equations for that anisotropic case, they reduce down to these equations. Notice the reflection is no longer a function of angle of incidence. So we still have not set reflection to 0 yet. That'll be the next step. But we did make it independent of angle of incidence. If we can somehow come up with another rule for A and B that makes those 0, then it'll be 0 for all angles of incidence. So we've removed the dependence of angle by making the square root of B times C being equal to 1. Well, so we'll set these remaining reflection terms with our new expressions equal to 0. And what comes out of this? Well, as long as we make A equal to B, we will get 0 in the numerators of these equations, and we will have 0 reflection. That's independent of angle of incidence, independent of polarization, and independent of frequencies. So the two rules we came up with to do this is that the square root of B times C equals 1, and we make A and B the same. So let's review what has happened here. We want to keep the impedance matched. So we'll set mu equal to epsilon. We'll just call this S. And at first we made it just a biaxial. We just put numbers, all three different numbers going down the diagonal. But then we came up with a set of rules that said A and B have to be the same. We also said that the square root of B times C is equal to 1. And that comes out being B is the reciprocal of C. So think about that one. So here's our conditions on A and B. So really what has happened, we have some arbitrary parameter here, some arbitrary parameter here, A and B are equal, and then this third term is the reciprocal of the first two. And so since we're absorbing energy going along in the z direction, we'll call this S sub z. We're going to want to make these complex numbers, right, because we're introducing loss and also controlling impedance, so we need two numbers in each of those. So here, the S sub z's take the place of A and B, and then the reciprocal S sub z we put in for C. And the subscript z is just reminding us this is for a wave traveling in the z direction that hits a boundary traveling in the z direction. And those numbers will be complex. But in 3 dimensions, we have waves that can travel in x, y, and z directions. We actually need all 3 at the same time. So we step through derivation of an S sub z, which is for a wave traveling in the z direction, hitting a boundary that's limiting the z-axis. We could have easily talked through a wave traveling in the y direction or a wave traveling in the z direction. And the reality is we want all 3 of these. So if we multiply all these together and come up with some big matrix S, this is what we end up with. And this is our uniaxial PML. And we're calling it uniaxial because if we look at this tensor, 2 elements are the same and the third one's different. That's uniaxial anisotropy. So this is called a uniaxial PML. And if we put all 3 of these together, this is what our PML looks like for 3 dimensions. And here's another visualization of it. So a 3-dimensional grid might look something like a cube, and you notice these PML regions, they actually overlap in the corners. But if we visually separate them, in the problem space, we're outside of the PML, all of these S terms will just be 1s. So in a way, it just sort of turns off the PML. And so nothing is interesting happening on the inside. However, let's say we're going into this z-axis is up and down, we're going into this region, suddenly S sub z becomes something other than 1, and it's complex because we're introducing loss and also controlling impedance. And so sz becomes something other than 1 in this region, and also the same thing down here. I could also say in the x direction, the S sub x parameter becomes something other than 1 in these extreme regions, and it becomes complex. And the S sub y becomes something other than 1 in these absorbing regions. And of course, where they overlap, we'll have 2 or even 3 parameters in the corners that are something other than 1. In the problem space, they're all 1. In the regions, these start becoming things other than 1 and becoming complex. So that's what it looks like. Now what we want to do is show how we can derive the stretch coordinate PML from the uniaxial PML. So here's our uniaxial PML, and we will post-multiply our permeability and our permittivity by the S. And so we end up just multiplying these together. So one thing we can think of for a uniaxial PML is that we're just modifying our material properties at the outer part of the grid. And for frequency domain models, that really has a lot of benefits. And this was how we derived our PML tensor for the uniaxial PML. Now let's move S. S was post-multiplying the permeability and the permittivity, so there was an S here. We'll bring it over to the other side of the equation. And now we're pre-multiplying this del operator by our tensor. So let's think about that operation. We're pre-multiplying our PML tensor with this curl operation. Remember, that's what the curl operator looked like. That's what our PML tensor looked like. If we work through the matrix algebra, this is where we end up. Now, something kind of magical happens here. Here's the result we got from the last slide. Notice we're taking the derivative of z, and multiplying this derivative is 1 over sz. So our little dz term, which is a differential width in the z direction, is being multiplied by s sub z. Our little differential in the y direction is being multiplied by sy. And in fact, everywhere dy occurs, the same thing's happening. It's being multiplied by sy. dz is being multiplied by sz. Here we have a dx being multiplied by sx, and another dx being multiplied by sx. So we always have an sz multiplying dz, etc. This is a stretching operation. It's really amplifying the coordinates. We have some noise terms out here, but just focus on what's multiplying the dz. We have a stretching operation happening. So for right now, let's realize that, for example, if we have a wave traveling in the z direction, we're hitting a z-axis PML, if you will, sx and sy will just be 1s in that PML region, except in the corners where they're overlapping. So if they're just 1s, we can cancel those anyway. And in 99% of the grid, that's just fine. And so these all cancel, and here's where we end up. And this really is the stretch coordinate PML. We're modifying our del operator, and since we have this sx, sy, sz essentially stretching our coordinates, we call it a stretch coordinate PML. Now the sx, sy, and sz are complex numbers, so in a way we're stretching our coordinates into this complex space, which is a crazy concept. If you ask me, I think it's kind of crazy. And had we just introduced the stretch coordinate PML at first, that wouldn't make much physical sense. Maybe we could believe it and use it, but we wouldn't understand it. So I think first deriving the uniaxial PML, which has a physical basis, and then jumping to the stretch coordinate PML, I think it makes the stretch coordinate PML easier to understand and easier to believe. Okay, so we've formulated up to the point where we have this sx, sy, and sz terms. What numbers do we put into those? We know they're complex, but what numbers do we use? So we will introduce loss through a conductivity term. We're going to call it a fictitious conductivity because we may also have a real conductivity in there that we're modeling devices with. So we want to introduce loss for our PML region. So I put the little prime superscript on the conductivity terms, and this is how we'll use it. So we'll use the theory of conductivity to understand how to modify those sx, sy, and sz parameters. We'll treat those, for example, we'll treat sx as if it is an epsilon xx, a permittivity. And we know very well how to incorporate loss into permittivity, and we can borrow that theory to figure out how to put loss into our S parameters for the PML. So it all happens through the conductivity. Well, in the problem space, we'll make all of our fictitious conductivity 0. We don't want any loss in the problem space. In the PML regions, that's when they become something else. And notice that we're grading it here. So we're sort of slowly tapering from the conductivity, the fictitious conductivity being 0 to being something else out here. We grade it and smooth it. In principle, that's not necessary. Numerically, it's very necessary. We want to ease into the loss region to prevent reflections. And so for these y-axis PMLs, it's the sigma y that goes from 0 out to something large. And in the x direction PMLs, it's the sigma x that goes from 0 to something large, working outward. So altogether, it looks like this on the left. And we do have regions where we overlap a little bit, but most of the time we're in these regions where they're not overlapping. So that is the picture of how conductivity is introduced. We still haven't answered the question of what actual numbers we give. Other than zeros at the beginning, what maximum value do we taper out to? And how does that taper look? Is it a linear taper, parabolic taper, or something else? So here's one way of doing this. We will let our S parameters equal this, and we're borrowing how loss is incorporated into a complex permittivity. A degree of freedom we're not playing with here are these real terms. We could play with those and have numbers other than 1 here. And that does have benefits when we start trying to handle evanescent fields a little bit better with our PML. And that's not a concept that makes sense now, but we'll get into that in the next lecture. But suffice to say, we'll just set those to 1, and we're introducing our fictitious conductivities into our tensor components this way. And so that really comes from electromagnetic theory. So how do we taper these? We know it's 0 in the problem space, and it goes out according to some profile up to some maximum value. Well, here's how we do that, or at least one way to do it. And so Lx will be the width of one of the PML regions. X is how far into that PML region you are. And so if we think about it, this ratio, x over Lx, will go from 0 to 1 as you go from the problem space side of the PML to the outer edge of the grid. This ratio goes from 0 to 1 in a linear sort of fashion. We raise it to the third power, and that gives it a curved type of profile. And then we multiply it by our free space permittivity divided by 2 times the time steps. So this is really the maximum conductivity value that will taper out to. So our conductivity will go from 0 to this value over the length of the PML. So that's just for the X PML. We also have a Y and a Z. So this is just one recipe that works for tapering that conductivity. So in our code, we will build a sigma X array across our grid, and we will build a sigma Y array across our grid for 2 dimensions. If it was 3 dimensions, we'd also have a sigma Z array, and they would all be 3-dimensional arrays. But for 2 dimensions, we just have X and Y. So the sigma X array has both the X low and the X high PML, so we're absorbing waves on both sides. Notice nothing is happening at the top and the bottom for the sigma X conductivity, fictitious conductivity. Sigma Y is the opposite. Nothing interesting is happening on the left and the right, but we do have loss at the top and the bottom of this grid. And for both cases, the fictitious conductivities will be 0 in the problem space and taper out smoothly to some maximum value. So once we build these, if you plot them to the screen, you should see something like this. So let's go back to this concept of these ratios. We have X over Lx, Y over Ly, and Z over Lz. These ratios simply go from 0 to 1 from the start of the PML to the outside of the PML. So for example, for the x-axis PML, we will start at 0 on the left side of the grid. We start at 0 here, and as we work outward, that ratio goes from 0 to 1. Likewise, on the right-hand side of the grid, that ratio starts at 0 here and then works out until 1 at the very edge. So those ratios just simply go from 0 to 1 from the beginning to the end of the PML. Now, in our finite difference time domain algorithm, we really don't work with X and L's, which are physical widths. Instead, we work with grid indices that go 1, 2, 3, 4, 5, 6, all the way across our grid, however many points we have. So, in place of this ratio, X over Lx, we could use little nx, which we'll use as our grid index that goes 1, 2, 3, 4, 5, divided by, in this case I'm calling it nx low. So this is the number of cells wide the x low PML is. And the x low PML is the width of the PML on the x low side, on this left side. At the right hand side we use a different thing, nx over nx high. And so we're dividing two integers and we still get a ratio then that goes from 0 to 1. So in our finite difference time domain algorithm we're really using these integers, not these physical positions. But when we write the analytical equations we use the x over lx. And so we have a similar argument for y over ly and z over lz. We're always using our grid index divided by the number of cells large the PML is. So these ratios all still go from 0 to 1 from the beginning to the edge of the PML. So this slide is intended to help you build this single sigma x array, which will have a PML at the left and the right. Now, it is a two-dimensional array. I'm just not showing the y dependence here because it's not a function of y. It only changes in the x direction. And so I like to fill this in with two loops. One loop fills in the left side PML stuff, and the second loop fills in the right side PML stuff. So let's think about this left PML. It goes from 1 to nx low. However, our numbers increase going from right to left. So let's set up a loop, little nx, that'll go from 1 to big nx low. So that's going to cover the entire PML region. But we're going to fill in our values going from right to left. So how do we do that? Well, we do it with this string of numbers here. So we start at nx low, that's over here. Then we subtract little nx. This is the number that will go 1, 2, 3, 4, 5 all the way through the PML. So 1, 2, 3, 4, 5, however big the PML is. And then we add 1. That way we don't end at a 0, we end at a 1. So, and then we fill in however we want to fill in our numbers for the sigma x parameter. So we can use the equations on the previous slide. Likewise on the right hand side, now we'll work from left to right. So we know the end point, it's big NX, that's the size of the grid. So where does it start? It starts at big NX minus NX high, and NX high will be the number of cells in the X high PML, and plus 1, because MATLAB starts at arrays at 1, not 0. So we set up our loop now, little nx again going from 1 to big NX high. So where do we fill in the numbers then? At nx minus nx high plus little nx. And that'll take us from left to right. And then we calculate our value however we do that. Same thing happens here, but just in the y directions, but the same loops. This shouldn't really be of any surprise. And the y low and the y high PML can be of different sizes. This is just a quick summary of how I build my PML. So I start off originally, and I set both sigma x and sigma y arrays. Remember, these are the fictitious sigmas. I set them all to zeros over the entire grid. So if my grid is 100 by 200 points, I've just created 2 more arrays that are 100 by 200. I then, in sigma x, I use 2 different for loops to fill in my 2 different PML regions for sigma x. I use 2 more for loops to fill in the 2 different PML regions for the sigma y, the y PML regions. So overall, there's 4 for loops that happen to fill in the PML regions because the different PMLs can be of different sizes. If they were all the same size, I guess we could cram this into one for loop, but then you wouldn't have the freedom to change their sizes. So I think it's just a little bit more complicated to use 4 for loops than just one loop, and it gives us some flexibility that can be useful. Okay, now we have a pretty good idea of our PML parameters. We're starting to have a pretty good idea of what it looks like when we incorporate that into Maxwell's equations, but there's some more details that we need to discuss about that. First, I want to justify why we're using a uniaxial PML here instead of a stretch coordinate PML. Really, state-of-the-art in finite difference time domain right now is a stretch coordinate PML. And in the time domain, that's more often called a convolutional PML because we have these complex numbers. And what you'll see is this becomes convolutions later on. So that's state-of-the-art. but I'm not really teaching that. I'm kind of pointing the way, but I'm not teaching that. And the reasons are, there's a follow-on course to this called Computational Electromagnetics, and it focuses on frequency domain models. And in the frequency domain, a uniaxial PML actually has some benefits. We can formulate an entire code and implement an entire code without thinking anything about a PML. And we can run it, we can test it, we can do everything. And at the very last step, we just build in some complex numbers into the outside of our permittivity and permeability arrays, the same ones describing our device, and suddenly we have a PML. Whereas a stretch coordinate PML doesn't work that same way. We actually have to take that into account into the formulation. So for beginners anyway, the uniaxial PML for frequency domain models offers some benefits that way. And since this is a first course, following this is computational electromagnetics, I think this offers better continuity, and that's why I'm teaching it. They argue that a stretch coordinate PML is a little more efficient. I believe it is a little more efficient, but I don't think it performs any better than a uniaxial PML. And so for the size of problems that we're doing here, this will not hold us back at all, and it will provide better continuity going into the follow-on course, computational electromagnetics. And regardless, I've told you now that the stretch coordinate PML really is state-of-the-art. And if you're writing a commercial code that you want to sell, you probably would want to go with the stretch coordinate PML. And it's not much different than the uniaxial PML. Everything you learn here will help you formulate and implement a stretch coordinate PML. So how do we incorporate this into Maxwell's equations? One thing that kind of gums up the works here is that we want to pull off our D equals epsilon E, our constitutive relation. And so we have to incorporate our PML a little bit differently. But this is our starting point, Maxwell's equations. Also, we're in the frequency domain. Why are we in the frequency domain? Because the PML is a frequency domain concept. We build it in the frequency domain, we incorporate it into Maxwell's equations in the frequency domain, and then what we'll do is we'll convert Maxwell's equations over to the time domain and then derive update equations. But we start in the frequency domain. So where do we incorporate it? Well, we post-multiply our permeability, and if we're not pulling off our constitutive relation or not having conductivity in here, we would be post-multiplying an epsilon term here. However, we pulled off that equation. So what we'll do is we'll stick it in, multiplying our D field. A little bit different than what we've seen in Maxwell's equations. This is not a physical thing, but it still numerically incorporates loss just fine. So this is how we stick our PML tensor into Maxwell's equations when we've pulled off our constitutive relation. And I guess I'll also mention, and technically it would be possible to put our PML tensor here. However, we pulled this off for a reason, because we want to monkey with this and maybe incorporate anisotropy or dispersion or nonlinear material properties or other crazy stuff. We don't want the PML affecting that. We want to keep this a nice, easy equation to make our code more modular and make it easier to incorporate different strange material properties. So it's very convenient to put that here. So here's where we are, Maxwell's equations in the frequency domain with the PML in there, and that one constitutive relation pulled off. So, first thing, normalize the electric field quantities. And we normalize them the exact same way, and here's where we end up. So, normalize Maxwell's equations with our PML tensors. It's useful, I think, at this point, to write these sort of in a matrix form. And so, the three equations we have can be written this way. I like this form because I can see inside the tensors, and for whatever reason it kind of helps me visualize the interaction between the different tensors here. So I like this form. It also helps when we expand these out into a set of 9 coupled partial differential equations. So rather than have full tensors, we're going to limit our formulation to just diagonal tensors. So our permeability will just be a diagonal tensor, our conductivity will just be a diagonal tensor, and our permittivity will just be a diagonal tensor. I'll say it again, it's not just as easy as incorporating off-diagonal terms. There's some other considerations that we have to take into account in our finite differencing. We may touch on that this semester. We definitely discussed that in computational electromagnetics, but it's not something we're going to get into here. And our PML tensors are already diagonal, so we just have diagonal tensors now. So on the left are our three governing equations, if you will, and then these are vector equations. We can expand these now. So here's our set of 6 coupled partial differential equations that include our PML terms. And we see the PML terms here, here, and here, and also here. But remember, we had expressions for Sx, Sy, Sz. And so, for example, Sx was 1 plus our fictitious conductivity x, sigma x, over j omega epsilon. So this is the reciprocal of Sx, this is Sy, and this is Sz. Sx, reciprocal of Sy, Sz. Sx, Sy, reciprocal of Sz. So all we've done is replaced Sx, Sy, Sz with those expressions containing the sigma terms. And this really is the final form in this lecture series of Maxwell's equations with a PML. In the next lecture, we will start with these, convert them over to time domain, do our finite difference approximations, and calculate update coefficients. Update equations. And we'll have a bunch of big ugly terms that collect into these update coefficients that now will be big and ugly now that we've incorporated the PML. And the last thing I'll leave you with is that the PML is not a boundary condition. It's very commonly called an absorbing boundary condition. It's definitely something we do at the boundaries. It definitely absorbs. But remember what a boundary condition is. First, we had our physical boundary conditions. That's not what we're talking about here. The physical boundary conditions were tangential components of E and H are continuous across the interface. The normal components aren't. That kind of stuff. We're talking about a numerical boundary condition where we have a finite difference equation at the edge of our grid that's using a term from the outside. That doesn't exist because we're not storing it. So that requires us to modify the finite difference equations at the edge of the grid. That is a numerical boundary condition. So that is a boundary condition. Notice the PML doesn't tell us how to handle that. All the PML is a way of incorporating loss in the outer few cells of our grid to absorb outgoing waves. Doesn't tell us how to handle that finite difference equation. So in fact, when we incorporate a PML, we still have a boundary condition problem that we have to solve. One of the most common things to do is to just use a Dirichlet boundary condition. If the PML is doing its job, the field is decaying, by the time it hits the boundaries anyway, it's essentially already zero. So that's the most common thing, not the only thing. There's other types of absorbing boundary condition. There's a Murr absorbing boundary condition. Those work pretty well. However, they really only work well for waves of one polarization, one angle of incidence, that sort of thing. But if we know that is the case, it works better actually than a PML. It's a little bit more efficient. So what does happen sometimes is a PML in conjunction with something like a Murr boundary condition. But in this class, we'll just use a Dirichlet boundary condition, and that's going to work just fine for us.